Welcome to my video tutorial on the Matlab program Chapter 3 OLG dyn1.m. This application is taken from my book on public economics from Chapter 3 on overlapping generations model. So in order to run the program you need a version of Matlab. Any version will do. You need to download my Matlab Computer Code from my homepage, and it would be helpful if you also download the slides that accompany my book Public Economics, in particular Chapter 3, the slides for Chapter 3 on overlapping generations. And in this tutorial here you learn how to compute this model with the help of a Matlab program. In the first part I will set out the economic problem before I turn to the Matlab code, which we go through line by line. This program here, this tutorial, is a good place to start if you have little prior or no prior Matlab experience. We solve the probably simplest problem in the book. So let us go to the slides that are provided on my homepage on Chapter 3 OLG model, and go to page 25 where the numerical example of sections 3.2 is explained. We study a two-period overlapping generation models with a young and an old cohort. The young cohort is working and saving for old age, and in old age the retirees do not receive any pension. As we consider only two periods, the period length is rather long, so amounts to approximately 30 years, and population growth at the rate n equal to 10%. So this amounts to an annualized population growth rate of approximately 0.3%, something that you observe in the United States more or less. We assume lifetime utility to be additively separable in utility today and utility tomorrow. So instantaneous utility in young age is given by the logarithm of consumption in young age, C1t, and utility in old age is given by the logarithm of consumption in old age, Ct, in t plus 1, and utility in old age is discounted by the factor beta. Now production is characterized by constant returns to scale. We assume a Cobb-Douglas function in capital K and labor L. We identify labor with the size of the young cohort n, simply assuming that each individual in the young cohort is supplying 1 unit of labor inelastically. As the production function displays constant returns to scale, we can express the wage W and the interest rate R as a function of capital intensity lowercase k, which is simply defined as aggregate capital over cohort size of the young agents NT. We parameterize the model as follows. Beta is set equal to 0.4, which corresponds to an annualized discount rate of approximately 3%. And we set the production elasticity of capital equal to 0.36, so that the labor income share amounts to 64% in our economy, roughly coinciding with the labor share in the United States. Due to our assumptions of logarithmic utility, savings are proportional to wages and do not depend on the interest rate. So the income effect and the substitution effect of the rise in the interest rate just cancel, and savings are given by equation 20 on the slides 26. Now let's turn to the capital market equilibrium, where aggregate savings at the end of period T are equal to the beginning of period T plus 1 capital stock. And this results in the dynamic equation presented in the first line of slides number 27. So in equation 21 we have a nonlinear first order difference equation of the capital stock, and this describes the dynamics in our model. In steady state, capital intensity is constant, so that Kt plus 1 is equal to Kt equal to K, and for our parameterization this amounts to K equals 0.06. With the help of the capital intensity we can compute the wage rate W, the interest rate R, savings S, total production Y, consumption in young age C1 and consumption in old age C2 in the steady state. Now our dynamic problem is to compute the transition dynamics for initial value of the capital stock given by K0, and we choose K0 to be equal to 1/3 of the steady state capital stock. The resulting dynamics are presented in the figure on slide 29, and as you can see the convergence is smooth, so starting from 0.02 in period 0, within 3 or 4 periods the capital stock almost converges to the new steady state value of 0.06. So this is the economic problem that we would like to tackle, and now we get to the Matlab program that helps us to compute this model. So for this reason, open your Matlab program and load the program Chapter 3 OLG dyn1.m. So for this, go to the Open menu point, open the program, and your screen should look something like this. Function Chapter 3 OLG dyn1, which is a starting function which is called if you invoke the Matlab command run. Now in the first couple of lines I introduced some comments. So if you find the ampersand after this sign, Matlab ignores all text, so this is used to insert some comments. So in line 2 I document what the computer program does. It computes the dynamics of the example economy, and I also specify the author and the last date it was changed. In line 8 we find a command CLC, which is the clear screen command. If you do not know a command in Matlab, you switch to the menu point home and can use a help function. So if you press help documentation in the menu bar, you can specify the command, let's say CLC, in the search window, and you find that this Matlab function clears all input and output from the command window display. So let us close this search function, help function again. If you are completely new to Matlab, it may be helpful if you use the tutorial that's also provided by Matlab in this menu bar. Now let's get back to the editor. We will go through this program line by line, and for this reason it is helpful to set a so-called breakpoint. So just move the cursor to line 14 on top of the minus sign and introduce a red dot, which is a breakpoint. So if you now run the program by clicking the green arrow, Matlab executes the program until he gets to the line 14, where he's waiting for your input. So to move on in the program, you just may press F10 or the green arrow in the top menu to go from line to line. So in the line 14 and 15 we have assigned the value 0.36 to alpha and 0.4 to beta. And you can also look up these values if you move the cursor on top of the variable. So we have created what is called a structure, par for parameters, and these are our global variables which we will pass on to other functions that we call. This is a very convenient way to deal with global. Another one would be to define global variable explicitly with the command global, and you will encounter this kind of programming in chapter 6 on pensions. Now let's proceed to step on. So we have assigned alpha, beta, the number of transition periods and the population growth rate in the first 4 entries of the structure. Now the next one is the steady state capital stock. The right hand side of this equation is the one you find on the slide below, equation 21, and we compute the value of production in steady state. For this reason, let's step in this function yy, which is the production function, and we pass the structure parameters which we will use for the computation of production per capita, k to the power alpha, and which, as you can see here in this part, so alpha is equal to 0.36, and we passed the value of the capital intensity for which we would like to compute the production as a variable kk, and this is equal to our steady state capital intensity 0.06. And to step out of this function, you just have to press the respective cursor step out. Now we continue in our computation. First, we initialize a vector kt with 21 zeros. This is, in kt, we store the 21 values of the capital stock during the transition. So the first entry will be our k0, the second entry will be our k1, and so on till k20. We initialize the first value of kt of this vector with k0, and it is equal to 0.02. Now we iterate over the equation 21, assigning for given k0, for given k0 we can compute k1, for k1 we can compute k2, and so on up to k20. This is done in the for and loop in lines 32 to 37. So here we assign the right hand side of the equation 21 to the next period value of the capital stock. This could be equally done by using a function. So let's step into this function, equation 321, which is provided in line 77. This is again the right hand side of the equation 21, and I advise you to use functions as much as possible if in your programming. If you, for example, use this right hand side in your computer program in many lines of the main program, and you find out afterwards, well, there's a mistake in the programming, and you would like to change any part here, well, then it's cumbersome to find all places where you have used it. It's much easier if you only use it in a function and correct it there. This helps you to avoid mistakes and errors in your programming. So let's step out of this function again, and of course this has the same effect on the value of kt2. It's assigned the value 0.04. Now we go through this loop 20 times, but this is a little bit annoying to press the step button 40 times. So let's just put the cursor on top of the command figure and press in the menu, press run to cursor. So we just run to the cursor and have assigned the 21 values to the vector kt, which stores the dynamics of the capital stock. Now in the next 4 lines we plot the dynamics of our capital stock. And of course, it is equal to the one displayed in the slides and also in the book. This is the first part of the program. Now go to the second part. Let's go to the second part where we compute the derivative of the first order nonlinear first difference equation, and check for the stability. For this, the derivative in steady state must be smaller than 1 in absolute values. So let's assign the steady state capital stock value 0.0606 to our variable x and compute the derivative in steady state as the slope of the secant. So we look at a point which is a little bit above the steady state, x1, and one that is a little bit below the steady state, x2. So the difference is 10 to the power minus 8 in both cases, and compute the value of the function g of kt at these points. And if we take the difference divided by the difference between the 2 points, we have the slope of the secant, which we will use as an approximation of our derivative in steady state. And we will find out that this derivative, our numerical approximation of this derivative, 0.36, is the same as the production elasticity of capital. And this is no coincidence. We show in the book that this is indeed the case for this model, that the derivative in steady state is equal to the production elasticity of capital alpha. Now we save our results in chapter 3 OLG dyn.mat and finish the program. So this, if we have saved the data and our results in chapter 3 OLG dyn1.mat, and we can load it into our working directory. So for example, if we want to see the values of our time sequence for the capital stock, we just press KT and you find here the values that we have just computed. So this will conclude our tutorial here on the Matlab program, chapter 3 OLG dyn1.m. If you have any questions, please do not hesitate to send me an email and I will try to answer you as soon as possible.